Okay, hello. Okay, welcome everyone. I think we can start. There is some people left, but okay, I think they will be coming in a while. Okay, I see some new faces, some old faces. That is great. I have to do one disclaimer before everything, is that these things have to be like give back when we finish the workshop, okay? In order to some people to not get mad, so please give them back. Okay, as I said, welcome everyone to another edition of the QTYR workshop. As the name says, is quantum technologies for young researchers. So this workshop is mainly aimed for being a kind and friendly environment for young researchers in master students and some PhDs especially, to present their new works in a place where there is not, this place is not full of PIs or old researchers, like experts on the field. We all are in the same place. We are starting our scientific careers. So please, I kindly ask you to be calm, to just present your work, because more or less, almost all the questions will be friendly questions. So yeah, just enjoy. So now I just have to, a couple of slides. As you may know already, we will have some invited speakers, some keynotes, some classes, lectures given that by some invited speakers. We also have contributed talks by some of you, and also a pair of poster sessions. So yeah. Then we will have a quantum industry focus session, which is organized by the people from the master's degree in quantum technologies from the CSIC, which is also a big part of this workshop. And well, I want to remind you that the social activity is in Parque Atracciones de Madrid. It is today. The ticket is free. I don't know. Someone asked me before if there was a free ticket to the Parque Atracciones. Yes, that is the activity. I mean, yeah. We will meet basically after Carlos' talk. We will all meet 10 minutes after the talk, more or less, here in the entrance. And the idea is to go all together to the Parque Atracciones, okay? In metro, or to go all together. Yeah, I think also in an email, someone reminded you that there are some places to leave your backpacks and everything in Parque Atracciones for, I think they are cheap, for a cheap price. Okay, and well, okay, it is sponsored by the university, School of Science and Technology. Then another social activity that we have is the conference dinner, which is on Thursday, in Tragabuches by Chef Dani Garcia. We have changed the place from the last year. We hope it is nice. I mean, it will be also new for us, but let's see. I think it seems to be pretty good. And it's sponsored by TalentQ and Archimea Research Center. And, well, before everything, I want to come back because I forgot to say thanks to all, in general, the sponsors and platforms that allow us to do this, to the Master Degree in Quantum Technologies, the WIMP, Quantum Space and TalentQ, Instituto de Física Fundamental, IQF, CSIC, Real Sociedad Española de Física, and the ICMM, okay? And yes, to finish, I think I just want to remember that the main people that are organizing this, and myself as well, and some colleagues, we are part of PISC, the PhD and Young Scientists Quantum Technologies Network in Spain. This is a young scientist networks that basically we organize this workshop yearly, and also we have monthly seminars, online seminars, that I encourage you to, if you want to scan the QR and fill the Google Forms to present voluntary to expose your work, it's also, you can also do it monthly. And yeah, I think now Diego from the master will give some words to all of you. So yeah, Diego.
Hello, hello everyone. Thank you for being here, and thank you to the network of young researchers for organizing this event. You know, this event is also the closing event of our master degree of quantum technologies. So that this master degree program is is originated from CSIC, yeah, together with the WIMP, the Universidad Internacional Méndez Pelayo. And we have several universities involved here. Let me see, Zaragoza, Valencia, La Laguna, Politécnica de Madrid, Politécnica de Cartagena, and Murcia. And then we have other 3 universities here which are not officially involved in the master, but some of us belong to them and have are teaching there in several courses. It's Sevilla, Vigo, and Granada. And we are supported by different national initiatives and platforms that you can see here. Yeah. Let me tell you a few facts of this master degree program. Yeah, we have 3 academic directors because we have a lot of students and a lot of teachers especially, and it's very difficult to deal with them. So first director here listed is María José Calderón from the Institute of Material Science of Madrid. Say hello, María José, so everyone knows you. Yeah, so she's the actual director of the master. And then we have David Sueco from Zaragoza. He also belongs to CSIC. And myself from the University of Seville. We 3 are trying to deal with this master that requires a lot of time and work. And so these are the few facts. So we have 60 credits, 60 European credits of teaching for passing the master program. It takes 1 year to go through it. Yeah, typically from October to July, first call, and September, second call. But it's optional. You can do it in 2 years, too. Yeah, just selecting different grades, 30 plus 30, more or less. And it's fully online, as some of you know already, with some optional laboratory courses. You can go there and do your practices if you want. I mean, there are elective courses. And, of course, this workshop, which is in person. We want every student to come here, visit us here, and enjoy this event. And everything's in English language. And our target is especially science students, especially physics. Yeah, but also we have several students that have engineering degrees. And I think they've been doing successfully. Yeah, so we did our best, and they did their best too, and pretty well. We started actually this workshop in the course 2022-23, and it started as a master in the context of the WIMP only. It's what you call in Spanish master propio. Yeah. So this was 2 editions, and then from this course we are finishing now, it's official master. That means that the credits you get are good for starting a PhD program afterwards. Yeah. And now it comes our 2nd edition as a official degree. It's 2005, 2025, 2026. And we can say that all vacancies are filled in first call. And we have something about 110 applications for 60 spots, which is pretty good, I would say. And we are now finishing with inscriptions and everything. And we plan to start this next October, I think. I think I'm not forgetting anything. That's all right. Okay, thank you everyone for being here, to the organizers and our students. Yeah. Okay, see you around.
Okay, hello everyone. My name is Mitchell, one of the organizers of this workshop that is about to start. I want to thank you all for coming here. And the first session of today will be on quantum materials. And I have the pleasure of introducing our first invited speaker, Alberto Bordin from Delft University of Technology to Delft. Some of us already know him well, and as well as his great work. Alberto defended his thesis entitled Engineering the QTYR chain, the first experimental realization of a QTYR chain with exotic Majorana physics. And now he's a postdoc in Leo Kammerhaven's lab. First, I want to thank you for coming here. And with that said, the floor is yours.
Okay, hello everyone. So I have the burden of the first talk, so please help me to tailor it to the right level. So no questions are stupid questions, no questions are too advanced. Feel free to interact with me at any moment so that we have a little bit of fun. All right, let's go. And first of all, I want to thank all the collaborators that are listed here. Today, I'm going to present mostly the work of my PhD, but this has been done in collaboration with a lot of people, and it wouldn't be impossible otherwise. All right. In quantum technologies, this is kind of our dream, right? To have a perfect quantum computer with perfectly infinite coherence qubits that we can control at wish. But actually, our reality looks more like something like this, with crappy, noisy qubits coupled to the environment. And the question underlying my research was basically, is there a way to use our reality and combine in such a way that besides the noisy environment, we can store quantum information degree of freedoms into objects that do not vary for small perturbations. And that's exactly what the mathematicians call the concept of topology. So that's the goal. And a simple way to do that was proposed 25 years ago by this guy here, Alexei Kitaev, who proposed to use a chain of n fermionic sites, like this, and wrote down a relatively simple Hamiltonian. There is, for every site, an energy term, and these are the fermionic operators for every site. Then there is a hopping term in between neighboring sites. And something a little bit more exotic, but not too much, is this C-dagger type of coupling, with a coefficient delta to recall the superconductivity, because you get this type of couplings with the superconductor, with the only tricky thing being the fact that the underscript here, it's n and n plus 1. So you want to create 2 electrons into neighboring sites, and that's maybe not that trivial. Okay, so this is the simple toy model Hamiltonian that Kitaev proposed. And what's interesting is that at the edges for certain parameter spaces, you could get these Majorana-bound states that live one at one edge and one at the other edge. But what are these Majorana states? To understand a little bit, we can follow Majorana's own paper from nearly 90 years ago. And what he did was simply to rewrite the C and C-dagger electron operators into their real and imaginary part. And this way, you get 2 other operators, gamma 1 and gamma 2. So the only thing that for now I would like you to remember is that 1 fermion is 2 Majoranas. And actually, if you do the exercise, also the other way around is true. So 2 Majoranas is 1 fermion, meaning that if you have 2 separated Majoranas, you can define a fermion this way, and you can verify that it satisfies its commutations, anti-commutations rules, and so on. So 1 fermion is 2 Majoranas. And these operators have a few properties that you can verify by inverting the relation. They anti-commute, they square to the identity, and the number operator, C dagger C, is basically the product of the two, plus a constant that we do not care about. And this is what we define as the parity operator. And I talk about parity because in a superconducting system, the total number of electrons is not conserved, but the parity of electrons is. So that's the only thing that we care about. And finally, you can see it very simply here from this relation here that they are Hermitian. And this has a few interesting consequences. The first of them is that they have 0 energy. And this means that we know exactly where to look for them in the spectrum. And if you remember one thing from today, it's better to be this one. So in all the following slides, we'll see a lot of spectra, and the states we are interested in are at 0 energy. That doesn't mean that every 0 energy state is a Majorana, but a Majorana must have 0 energy. And other important properties is that they have 0 net charge and spin, which means that they have a hard time coupling to electric and magnetic fields. And even more interestingly, Keytev demonstrated, proved that if you manage to bring them far apart, then they cannot couple to any local perturbation of the Hamiltonian. And that's why they are interesting to us. That's when they are far apart, that's when the topological nature comes in. But there's more to that. It's not only about having a state that is well protected. And the interesting thing is looking at what happens when we try to exchange them. And Ivanov here in this wonderful paper proved it very nicely. And he just considered 4 Majorana excitations. So you can imagine that these ones define 1 fermion, and this one define another fermion. And we can count the amount, the number operator for the 2. So let's say we initialize the system in the 0-0 state. So 0 electrons here, 0 electrons here. And then what he proved is that if you exchange the middle 2, then if you do it twice, you go from this 0-0 state to this 1-1, which we can define as a logical 0 or a logical 1 of a qubit. And doing only one exchange brings you into this superposition. This means that these operators here, these quasi-particles here, they're not fermions, they're actually anyons, because when we exchange them, we get a non-trivial phase. And what's, I think, very interesting is that when you exchange them, then you realize a perfect 90-degree rotation. And that's something that it's sometimes overlooked in quantum computing. So it's not only, the task is not only trying to have qubits that are as long-lived as possible, but also to calibrate well all your gates. And that's why Google has better processors than IBM. IBM has better qubits, but Google, they do a better job at calibrating them. Because indeed, right now, quantum computing is still analog computing. And if we manage to get at least some gates, not all of them are doable like this, but if we get at least some gates with these exchanges, then we turn at least part of the quantum computation from analog to digital. And that can be a revolution like the transistor was after the valves, for instance. So that's what we ultimately work towards. All right, now let's go back to the key-type Hamiltonian and try to understand how we can create this isolated modes at the edges. And the core of the idea is simple. So you can imagine to write down the operators for every site and do this trivial change of basis of just writing them down in the Majorana basis. And like this, nothing happens. It's just a math trick. You're writing the same Hamiltonian with a different with different operators, but it's the same thing. What's interesting is that if you manage to couple somehow in this way, then you end up having two isolated Majoranas at the two edges that define one non-local fermion living on the left and on the right side of the device. This is the idea, and right now is only a picture, but in a few slides it will become maths and measurements. And to do so, the ingredients that we need is to have tunable couplings to be able to go from this scenario to this scenario. And of course, we would like to have the chain as long as possible, because the more these Majoranas are far apart, the higher the protection. All right, so our goal is to realize this toy model. I think this is a very fun exercise. It's just Hamiltonian engineering. And a lot of people do that, for instance, with trapped ions or neutral atoms. And this is how we do it with electrons. And what we want to do is indeed realize every piece here. So we want a mu term, we want a controllable t term and a delta term. But also, if you pay attention, here in this Hamiltonian, there is no summation over the spin degree of freedom. Indeed, this Hamiltonian assumes a spinless chain of electrons. So we want to find a way to somehow lift the normal spin degeneracy that you have in electronic systems. So a standard way to do so is adding finite magnetic field, put some Zeeman splitting, and you're done. And then we want some tunability to get to this scenario. So in the following slides, I will show you how we can make this in an experiment. Let's start from the beginning. So from the mu term. We want to have sites, so confined spaces where we can put electrons, and we want to be able to control their energy. So it's very natural to use quantum dots to do this. And in particular, we do so using semiconducting nanowires. A nanowire of ours is 100 nanometers thick. So you're already confined in two directions, and you only have the longitudinal direction left. And you can place the nanowire on top of a dielectric, on top of an array of bottom gates, which you can use to tune the every region of the nanowire, choosing which parts isolate and which parts conduct. So you connect all these gates to voltage sources, you put a source in the drain, and basically you have a transistor. You can put a little voltage bias, measure the current, raise tunneling barriers here, and that's how you get a quantum dot. And in the end, once we have the system like this, we only care about this gate who's controlling the energy of the quantum dot itself. And then we measure it like this, put a little bit of voltage bias and measure the current. And this is such an example of such a measurement where you can see single states appearing. The current here is directly proportional to the density of states of the system. So as we move this gate, we see the states popping up 1, 2, 3, 4, and so on. And you can really count them and like map them like to an artificial atom. So this will be like the s orbital, this will be the p orbital, and so on. And what happens if we put them next to each other? Well, instead of having just a single trace like this. We can have a 2D map, still measuring the current. And you can imagine to cut it like this or like this. These are the gates underneath the 2 quantum dots of this device here. And basically what you can measure is this, the peaks as I was showing you before, and you can count the amount of electrons that you have in the system. And in particular, you can also focus on, say, one of these Evoli crossings and count the charges for every electron that you have in the system. So here you have 0 electrons in either quantum dots, here you have 1 in both, and here you have 1 in the right and here 1 in the left quantum dot of this system. So basically, with this, we just realized this part of Hamiltonian. We are able to do a chain of quantum dots, put them next to each other, and control their energy here by just sweeping this gate. And in addition, we also get something else for free, which is here you see typically a little bit of a voided crossing, which means that there is some coupling between these 2 states. So typically, you get also a little bit of T coupling for free. The only thing that is missing is the delta coupling, as indeed it's a little bit more exotic. So the way to do so is to add a superconductor. And as I was saying you at the beginning, the tricky part is that you want to put 1 electron into one site and another electron into the neighboring site. So the device that you're after is called a Cooper pair splitter. So you have Cooper pairs here in this superconductor, and you want to split the Cooper pair and put an electron here and an electron here. This was demonstrated in this wonderful paper. And we basically tried to reproduce that to have this same type of coupling in our system. But with one difference. And the difference is that instead of using a bare superconductor here in the middle in between quantum dots, we use a semiconducting superconducting hybrid. And that has quite some advantages that will be more clear later on. This was shown in this paper here. And to give you a little bit of an idea of what happens, I have these slides here. Here is the device where you can see the nanowire, the little aluminum strip on top, and contacts on the sides to measure it. And here the keyboard of gates below that you can use to define quantum dots here and here. And this is a sketch of the same device with the superconductor in the middle, a Cooper pair here. And if you put the biases in such a way that they can accept electrons, then you can split the Cooper pair and resonantly go put 1 electron here and 1 electron here. And this happens only if the energies of the 2 quantum dots are equal and opposite. And that's why where you measure the current that you get in these leads on the left or the right as a function of the quantum dot energies on the left and on the right, you see an anti-diagonal line, which means that indeed the 2 energy must be equal and opposite in order for you to get some signal. All right, so to summarize, here in this work we demonstrated that this is possible, so to detect a finite amplitude of this splitting of Cooper pairs. Normally we call it cross-Andreev reflection because it's equivalent to the reflection of an electron into a hole and vice versa. So we use that as synonyms: cross-Andreev reflection, Cooper pair splitting, or delta. And what's nice is that in this system, also the tunneling term comes at the same time, basically for free. And here, instead, if a single electron tunnels between the 2 sites, you need to conserve the energy, so the 2 energies must be equal, and therefore you get a line that goes along the diagonal, not the anti-diagonal. And this shows that you can get both processes in the same device. Since this is a tunneling through a gapped system, we normally call it co-tunneling or elastic co-tunneling, or ECT for short. So also in the future slides, I will just use T and ECT as synonyms. But there might be a little problem, and it's if we add a magnetic field that we need in order to split the spin degeneracy, can we still have T and delta, so elastic co-tunneling and cross-tunneling reflection, at the same time? And the problem is that if we shuttle a single electron from one side to the other, normally the spin is conserved. So you can only move spin-ups into spin-ups here, for instance. And if you instead split the Cooper pairs are singlets. So you get an up in one side and a down in the other side. And I need to remind you that these quantum dots select the spin. So you either tune the quantum dot to accept spin ups or to accept spin downs. You cannot have both at the same time. So how can you have these two processes simultaneously? And the trick is to use a material that has a little bit of spin orbit coupling, which couples the spin degree of freedom with the momentum degree of freedom. And so that when the electron travels, as it travels, its spin precesses. And therefore, at the end, there is a finite probability of ending up spin down or spin up for either process. To convince you on this, I have this picture, which shows the amplitude of spin flipping elastic co-tunneling. So the forbidden process, in theory, which it turns out to be possible if you have a little bit of spin orbit coupling. And the amount of signal is detected in blue, and this full sphere is it's basically fully blue, which means that in almost all configurations you can get some finite elastic co-tunneling signal. There are only two white spots here, and this corresponds. So this globe here is represents all the directions of the external magnetic field. This B here that we can add, and we see that in some directions here and here, the spin flipping process is suppressed. And that happens because you can actually model the spin orbit coupling as an effective magnetic field, which makes the spin precess over as it travels. But if the external magnetic field is parallel to the spin orbit field, then no precession can happen because you have your quantization axis along that way. So this is another verification of indeed this spin flipping process being enabled by spin orbit coupling and not something else. All right. So it seems that we have all the ingredients. We have the mu term with quantum dots. We have the T term with the elastic co-tunneling. We have the delta term with cross-tunneling reflection or Cooper pair splitting. We can put a magnetic field and retain the two processes at the same time. What we miss is the tunability. And that's what brings me to the next section. Any questions so far? Yeah, so that's actually a very good question, and we are actually quite lucky because in the end, the point we care about is at zero energy. So when you are at zero, you have the energies equal and also equal and opposite. So it's exactly the point where you can have both processes at the same time. But in practice, even if you are a little bit off, as long as you're off by less than the coupling terms, you're still fine.
What about the coexistence of magnetic field and superconductivity? What's the trick here?
Thanks also for this question. So, indeed, usually if you put a big magnetic field, then you kill superconductivity. So what we want is to polarize the quantum dots before the superconductivity is killed. And so we choose a material for the semiconductor that has a high G factor. So it gets a big energy splitting as the magnetic field is increased. So you have the Zeeman energy being G, Bohr magnitude, and magnetic field. Let's put the models here. And we choose a material, indium antimonide, that has a G of about 45. And whereas, for instance, the aluminum superconductor that we use has a G of about 2. So we are much faster. And but actually, this doesn't matter much, because the only thing that we care about is having this bigger than the temperature. So as long as this guy is bigger than kBT, we're happy. And in practice, that happens for us at a few hundreds of millitesla. So 100 millitesla is fine, and aluminum, even if you put the field out of plane, typically sustains that. But you can go even crazier, because if you make a thin superconductor, then you can sustain up to 2 Tesla or even more. So there is actually quite some window, which opens up the freedom of also using materials with less spin-orbit coupling to achieve the same result. Okay, maybe I'll go on a little bit and then stop for questions in a while again. So as I was saying, the only missing ingredient is the tunability. And I want to show you why here it's important. And let's do the exercise for just the simplest key-type chain Hamiltonian of just 2 sites. So here we have the mu terms, mu1 and mu2, the tunneling terms, and the delta like terms in blue. And what's nice for us dumb experimentalists is that we can map this Hamiltonian into a diagram, which we can draw. And this happens because, as I was showing you in one of the first slides, this product, gamma 1, gamma 2, is basically the C1 dagger C, which is the term that is next to the mu. And if you do the same math for the gamma 2 and gamma 3 and gamma 3, gamma 4, you get the correspondence to T plus delta and to T minus delta. So in the end, you can view this Hamiltonian as exactly this diagram where the pairing between neighboring Majoranas is represented by these quantities here. So mu1 here, mu2 here, T plus delta, this diagonal, and this T minus delta, this anti-diagonal. Which means that if we go to the condition, and here we go back to your question before, if you go to the chemical potentials being 0, so that you have no red couplings anymore, and you put T equal to delta so that you have no, you don't have this bar anymore, you end up having this scenario, which has precisely 2 isolated states. And this is a very simple and easy to understand example. And if we manage to do this, we can get exactly 2 Majoranas that are not very far apart, but they are, in theory at least, perfectly separated. So you have 1 Majorana in one quantum dot and 1 Majorana into the other quantum dot. They have 0 overlap if you are at this condition. However, this is just a special point, so that's why we normally call them poor man's Majoranas, because they are not topologically protected. As soon as you deviate from this condition, you start to couple them. So let's try, for starters, to get to this condition in a real system. And for that, we need to be able, this is easy. This I showed you already in the first slides. When you just move the gate of the quantum dot and put the lever wherever you want, and you can put that to the point where the mu is equal to 0. That's easy. What's hard is to get this condition. And we were, again, quite lucky, to be honest, because we found out that if we move here the electrostatic gate underneath the hybrid, then the amount of cross-under reflection and elastic tunneling that we measure varies a lot. And both processes are substantial. Here we get fractions of a nanoamp of current. And they vary a lot. And we noticed that the highest modulation appears when something happens within the gap of the hybrid. This is just a measurement showing a tunneling spectroscopy of the hybrid. So we have here 0 energy. Here at around 0.3 there is the aluminum gap, which in case you put some magnetic field becomes a little bit smaller, but as long as you stay below 1 Tesla, it's fine. It's basically this. And here below the gap, there are some sub-gap states, that appear exactly where we see the highest modulation. For instance, here and here and here and here. So we try to investigate it a little bit more, and in this sub-gap states, we call them Andreev-bound states, ABSs. And we try to look at them more carefully and notice that if we look at the delta and t terms that we get around this gate values, we have regions here marked in blue where the delta is, where the car is dominant, and regions here in orange where the tunneling is dominant. And if we, at the same time, in the orange region, we take a charge stability diagram of the quantum dots on the right and on the left, then we see an avoided crossing, exactly as I was showing you at the beginning. And if, however, we go to the blue region here, we see an avoided crossing into the opposite direction, which is something that you do not find in normal double quantum dots. This is really coming from the superconductor. And this tells that there is some coupling between having 0 electrons into both quantum dots and having 2 electrons into the 2 quantum dots. So it's indeed something that creates or annihilates electron into neighboring quantum dot pairs. And since we can vary from one scenario to the other scenario with continuity, we can go from the scenario where we have the delta bigger than t to the scenario where delta is smaller than t, passing through a point where the two are roughly equal. And that's exactly where the poor man's Majorana sweet spot happens. And only here, if we take the energy spectrum, if we measure the energy spectrum of the system, then we observe 0 energy states. If you are at other positions, you can see them here. So at the center of this cross is the points where mu1 is equal to 0 and mu2 is equal to 0. That's where the dots are on resonance. So here is the point where you want to be. And when the two couplings are equal, here there is obviously a state, here a peak, but here there isn't, and here there isn't. So we see the appearance of 0 energy states only when this condition is met, where t is equal to delta. And we see them appearing with the correlation at the left and right side of the chain. So of the 2 quantum dots, here in orange I'm showing the conductance, which is the derivative of the current, on the right quantum dot, and here in blue on the left quantum dot, and in both cases they show a peak. We can do that also in another device. Here it's a little bit more clear because the gap between the 0 energy state and the first excited state is bigger and more visible. Again, we can get to this crossing point where when the two processes are balanced. And what's actually interesting is that these poor man's Majoranas still have a little bit of protection against some kinds of perturbations. And one perturbation is just putting a little bit of coupling in one of the two quantum dots. And you can do so by just moving the quantum dot energy. So in this case, the mu2 is no longer equal to 0, but varies a little bit. And still what we see is that a zero energy state remains for the full range. And that's basically because this Majorana is still isolated. And since 1 electron is 2 Majoranas and 2 Majoranas is 1 electron, Majoranas always must come in pairs. And if there is one isolated one, then there must be another one somewhere else, which guarantees that they still are at zero energy. If, however, we move both chemical potentials away from zero, then the zero energy state disappears and it starts to split quadratically from this point. And it's even worse if instead of changing the quantum dots, we change the T and delta. Here we see a picture measured in a different way, but basically the same thing I was showing you before, with a little bit of dip of this T coupling and a peak of this delta coupling. And here it's the spectrum of the system. And we can see that there are zero energy states only here and here. And everywhere else, the system is has more than zero energy lowest state. And here there are zoom-ins. These black points is where the Majoranas are, and then they split linearly. That's why we call them poor man's. And so in the next slides, what I will show you, and I'll try to be a little bit fast, is to how, and this was basically the main task of my PhD, how we try to go to, let's say, poor man's Majoranas to working class Majoranas. So to try to make the chain longer and longer. And to show you the importance of this, I made this simulation here when I show basically this splitting. And here, where these arrow points is where the Majoranas are, and here they split linearly. But if you do the same exercise in a 3-side chain, then in the spectrum you get a stable zero energy state, even if you change one of the couplings. And that's because this Majorana stays isolated, and therefore there must be another one, and so on. And you can also notice that here the T2 must be equal to the delta 2, but they are not equal in general to the delta 1. So you don't need to make all the couplings equal, you just need to balance it pairwise. So we went to the clean room and fabricated this device. Here there is a sketch and here an image of that device. We can have quantum dots, connect the contacts to sources and leads, and basically do the same story again. So try to see if we can get a mu term with normal quantum dots, and here they are. If we can get T and delta couplings, and here they are. And they are shown in this paper here, where we can pinpoint in every current signal where they're coming from. If either a double ECT process, or a double cross-under reflection process, or a mixture of the two. All right, so the only thing that is left is try to tune them to have this balance pairwise for every pair of neighboring sites. And we can do that piece by piece. So first, we do that in the left two quantum dots by setting the third dot of resonance by more than anything else in the low energy spectrum, so that it doesn't matter in the Hamiltonian. And we do the same game. So we tune the system until you go from one type of a body crossing to the other type of a body crossing until you get a cross. And here is where the zero energy state appears. So this is our poor man's Majorana for the system. It's actually this one. And if we move them away from zero energy together, then you get this quadratic splitting. And we can do that in the same way for the right side. So you get the poor man's Majorana here as well. And what is interesting is what happens when you put all dots together on resonance. Here I'm showing the same picture of the previous slide. So the two dots here are tuned with the T1 and delta 1 balanced. And then as the dots are moved away, so the chemical potentials are varied, the peak is split. But then if we just put the third dot on resonance, then the zero energy state stays for the full range. And I like this trick very much because you're measuring here on the left, and you're moving a quantum dot that is 2 sides away. Other than that, these two measurements are exactly the same. So there are 11 gates in the system, 4 contacts. All the 4 contacts have exactly the same values. All the measurement, the electronics is exactly the same. And all the 11 gates are exactly the same, but the one gate that moves the energy of the third quantum dot. And you're measuring from the left, and you're observing such a difference, which means that this whole system, these 3 sides, is a full molecule, and it's a highly correlated quantum system, so that if you move one side, you're affecting everything. And it's only when you move all of them that you get a little bit of splitting, also in the 3-side case. So in this sense, it's working class Majoranas is not yet fully topologically protected. We can only see a little bit of more protection, but if you look carefully, it's better than the 2-side case. And more importantly, let's look at what happens if you change T and delta with, again, this hybrid gate. This is the picture I was showing you before, a linear splitting. And here, again, the reproduction of the same thing in this device. And this is what happens if we put the third dot on resonance. A state stays at 0 energy for the full range. And that's why I think this is the biggest improvement, because you go from a linear splitting to a case where no single coupling can couple the 2 edge modes. You need to draw at least 2. All right. And based on this, we also did some back-on-the-envelope calculations to see, okay, if we want to make at some point a real application of these things, how long does a chain need to be in order to be useful? And so what we did is we looked at the dispersions of our measurements. Oops, sorry. So what happens when you put a little bit of noise and move them around. We looked at the precision of our voltage sources to see how precise we can tune them to the system. And we calculated the energy splitting that we get in a noisy case. And we saw that the energy splitting drops really exponentially as the number of sites is increased. And it's, I'm sad that I don't see the lines here, but it's very rapid. So you go from 1 to 1,000 in just going from 3 to 5 sites. It's really fast. And if you compare this to the typical coherence times of popular qubits, you see that already at 6, 7 sites, you start to become very competitive compared to other platforms. So in this sense, also this approach with really handcraft Hamiltonians can yield reasonable results within a human timescale. Of course, there are also other sources of noises in the system. It's not only what comes from the imprecision that you might have in tuning the system. For instance, you might have, and here I'm just saying it for the experts, you might have some quasi-particle poisoning in the system that mixes your, that brings you away from your parity manifold. But we're also working on that to try to move this barrier further down. And we actually succeeded in this, and we are preparing a paper. Next, I want to show you something a bit more fundamental. And this comes from an experiment done mostly by this colleague of mine on a different system. This is a 2-dimensional electron gas. So instead of having a single nanowire, you have a plane of electrons. And so you need to confine it then in 2 directions in order to have a chain of quantum dots. but they managed to do so. And here is the sketch of the zoom in of the final device with a quantum dot here, a quantum dot here, and a quantum dot here. And the additional freedom that you get if you can use a 2D system like this is that you can put probes wherever you want. And here they have a probe here, a probe here, and a probe here. And so they can measure the density of states in the left and in the right exactly as we did. And here, when you tune to the Majorana sweet spot, you get zero energy state in the left, a zero energy state in the right. But on top of that, they can also measure the middle, and they observe that there is no state in the middle. And this is probably my favorite result, because it really shows something that in topology in condensed matter is very fundamental. So having a bulk, here we don't have really a bulk, we just have a single quantum dot, but it's the beginning. You have a bulk with a gapped system, you don't have zero energy states, and then you have zero energy states at the edges. And this bulk edge correspondence is really ubiquitous in topology in condensed matter, even in other types of systems. And in the end, this is exactly where the protection of the edge modes is coming from. Because these low energy states cannot couple if not via hard virtual tunneling through the middle. Then we also did an exercise proposed by some people here in Madrid, which is, well, if topology is robustness to local perturbations, okay, our chains are not maybe fully topological yet, but let's see how protected they are from small local perturbations. And the simplest perturbation that you can put to the Hamiltonian is to just add one level. And that's provided by an additional quantum dot. So here, we just tunnel couple an additional quantum dot to a 3-side chain. And this is following the papers proposed by a bunch of people, and you might recognize a few faces. And the idea is simple. So if the Majoranas are separated, then the quantum dot, which is a local probe, can only couple to one of them. And if instead they have a finite overlap, then the quantum dot may couple to both, and therefore lead to energy splitting. So we produced this device, which is slightly different than the one I was showing before, because it has more space on the sides so that you can define additional quantum dots. And here I'm showing in red the additional quantum dot, and in green the quantum dots of a 2-side QTYR chain defined in this portion of the system. So what we do is this type of measurement. We have the third dot non-existent, and or off resonance, and we move the energy of this red quantum dot until it goes on and off resonance with the rest of the system. So it goes to a coupling scenario and goes away from a coupling scenario. And what we observe is that the zero energy state stays there for the full range. And this is good evidence that the two Majorana states are really separated. And what's nice about this QTYR chains is that you can detune the system on purpose to have your control experiment. So if you, let's say, move one dot away, then you start to have a little bit of Majorana overlap here, or even if you move both of them. And in both cases, here we do observe a splitting, which comes in two different flavors, diamond-like and bow tie-like, as they were dubbed by, by these people here. And they also match the simulations that my colleague Juan did. So it seems that also here everything checks out. We did the same exercise also on a 3-side QTYR chain, putting a third dot on resonance. And again, as we move the additional quantum dot, there is no visible splitting of the zero energy state. And as we detune some quantum dots, still there is no splitting of the zero energy state, which indicates that somehow these 3-side chains have a little bit more protection than the 2-side counterpart. And it's only when you detune at least 2 quantum dots from the resonance condition that you start to have a little bit of splitting. All right, a little bit of summary. So we could engineer the type chain getting the mu term, the t term, and the delta term. We were able to balance the t and the delta term, and here there are some examples. We were able to show that if you scale the chain up, then you get more protections against perturbations in various forms. This comes from having a bulk gap in the middle. And also if we, on purpose, put a local perturbation with this red quantum dot, we can see robustness. So all very nice, but I promised you at the beginning that everything here was towards quantum computing, right? So I would like also to show you a little bit of progress that we are making to realize a first qubit with these systems. But let's take maybe a couple of minutes break, and if you have any further questions, this is also a good timing.
I have a question regarding the scaling up the QTYR chain. Do you expect some even-odd effect depending on the number of quantum dots?
Yes. Yes. You can see that a little bit. There is a paper from Ezawa in 2024. Here you can see it a little bit. So you see that this is not a straight line, but it moves up and down a little bit. And that depends on the amount of noise that you have on the t and and delta or the mu terms. So if you have what was it? Yes. So if you, I don't remember which way it is. I think if you have more noise in the t terms, then it becomes way more even odd. Okay. Yeah. But indeed, you can input that in the simulation and see from which parameters you get. Yeah, so here to get this, you tune to the sweet spot, and then you put some perturbations here and there, and you average the energy splitting that you get. Any more questions? Yeah, they are. They are. So it's something that we discovered on the way. And initially what the theorists told us is, yeah, if you just ground your superconductor, it's fine. But in practice, no ground is a true ground in experiments because they go through room temperature electronics and so on. And you can get a little bit of voltage differences, maybe from thermal voltages or things like that. So in the end, if you keep these two aluminum strip separated, then you might have a little bit of difference in between the two. And if you have that, then the Josephson effect comes in. And that leads to a fast precession of the phase between the left and the right. So in order to stop that, just make a loop and connect them all together. I skipped on these details, but indeed that's also what we did at some point. So in our first device, in this device, we didn't have the loops connected. So, and that's exactly why here you get some blur, because you're averaging over many phase configurations. It's actually quite fine because as long as the phase is not pi, you have a finite gap. So there's only one point in phase where things go wrong, and if you average them, you don't see it that much. But if you want to make really qubit experiments, it's good if you fix your phases, and that's what we did in the second device. So in this one, and also in this one. Here I cut it, but actually here there is a loop connecting the two. All right, then I will spend about the next, how much time? I have 35 minutes, right? Or so? Okay, good. So let me spend 10 minutes on how to make a qubit. It's not there yet, but we're working towards it. And what does it take to make one? Well, we need to fabricate a device, and we need to have a way to manipulate the qubit. And today I'm going to show you a little bit about the fabrication and a little bit about this part of the qubit operation, which is the readout. And this is really super recent work. This we uploaded it on archive a week ago. And we hope to get here and here as soon as possible as well. Let me spend just a couple of words right now on the fabrication. There are more slides later, but now for the rest, I only need the fact that to make a qubit, we need 2 chains. And that's because in the superconducting system, the total parity is conserved. And therefore, you might define a qubit, but you wouldn't be able to make any gates within it. So in order to make gates, you want to have some redundancy and have 2 chains so that you can shuffle the parity from one to the other and vice versa. So just to remind, to make a qubit, we need 2 chains, so 4 Majoranas. The rest will come later. But first, let's focus on the readout of the parity of a single chain. And this we can do, and this is something that has been developed very recently by some colleagues of mine. And we can do that in 2 ways. One, sensing it through the superconductor, and one sensing it through this yellow normal metal lead. This is easier to understand because it's just coupling to another quantum dot, which is similar to the quantum dot test that I was showing you before, right? So you just add an additional quantum dot here, this charge sensor on the right of the device. The only difference here is that it's not tunnel coupled, but it's capacitively coupled. And that's important because if you want to preserve the parity, then your system must be isolated from the environment. You cannot afford to put electrons in and out to probe it. So here we have an additional quantum dot used as a charge sensor and only capacitively coupled to the 2-side Key-type chain. And this is as I was telling before, it's a very local probe. So somehow also limited. But also we have a global probe thanks to this superconductor in the middle. And this happens through a technique that it's called quantum capacitance. The idea is the following. So you put an AC signal to the superconductor so that you move it fast up and down. And this couples well to putting electrons in and out of the 2 quantum dots at the same time. So it couples very well to Cooper pair splitting, but it doesn't couple to the elastic tunneling. And since the Cooper pair splitting is what couples the even manifold, and the tunneling is what couples the odd manifold, in practice what you get is parity-dependent signal that is null for the odd parity manifold, and it becomes finite for the even parity manifold. And you can detect that. This is an example of such measurement. In yellow, we have the background. And in orange here, these ribbons happen when the quantum dots, you can see that they are a little bit more highlighted at the edges, and they happen when the quantum dot reaches the gap edge. And therefore you can tunnel single electrons in and out. But within the gap, so within this band, the biggest signal comes here in these anti-diagonal lines. And again, at the beginning of the presentation, these anti-diagonal lines means quantum dots that have equal and opposite energy, and it's again something that goes well with cross-sectional reflection or Cooper pair splitting. Here we have a zoom in of this resonance, and what you can see is that here the signal is very pixelated. And that's not a bug, it's a feature, because the parity is actually switching from even to odd and back many times due to indeed quasi-particle poisoning. This might be a little bit more for the experts, but I wanted to give something to everybody, so I hope the rest do not fall asleep too much. So here we can indeed measure some parity switches from the even to the odd and vice versa, and we can detect it in the form of a two-level signal when we do a time trace. In this device in particular, we observe switching time of about 2 milliseconds. And if you put this time trace in quadratures, then you see two blobs. And this means that you can distinguish between the two parity states with a single shot measurement if it's long enough. And long enough means 40 microseconds in our case. So in 40 microseconds, you can tell if you have an even or an odd state, an even or an odd amount of electrons. So ultimately, if your qubit is in 1 or 0. And we can do that both with the quantum capacitance technique and also with the charge sensing. But with the charge sensing, since this is a local probe, nothing happens. We observe just noise. And what's interesting, and it's a good verification for us, is that if you put on purpose the chain a little bit off, then the two signals, here a signal appears, and the two signals correlate very much. So indeed, we are quite confident that we are observing the same thing from just two different points of view. And the point of view of the charge sensor is enabled only if the chain is detuned. All right. We also have some preliminary data when we put two chains together in a qubit configuration. Here we do the same thing, but now instead of having switches between two levels, we have switches between 4. And if we put this in a quadrature, we see the blobs, and there are 4 of them. And this corresponds to both chains being even, both chains being odd, and these two blobs in the middle, one chain even and one chain odd. So indeed, it seems that we have all the capabilities to read out the system. All right, now we can take a little bit of a longer break, and I will reserve the last 25 minutes or so to show you a little bit about how we actually make these devices in real life. So what a PhD student life looks like for real. Any questions? Okay, the quantum capacitance was too much. You can ask also on the rest, or you can just rest. That's also fine. So we model it as a no Markovian process. So with the hidden Markovian process, but we don't know. I mean, this is just the model that we use to fit it here. Yeah, with 4 it's a mess. With 2 it's better because indeed you can model with the hidden Markovian model, and that's what this switches are identified with. With 4 it's a mess because when you switch from, say, this orange to the green, and maybe you pass to the middle or you're not, it's hard to distinguish. So we still need to figure out a little bit how to analyze this. Yeah, exactly. Well, depends, or vice versa, depends on how your resonator shape is. So I think you can't. So it might be all mapped opposite. And that's because your resonator might have a weird response. So practically, yeah. What you can do is to compare it with the charge sensor, because there you can distinguish. And so looking at this, you can map what this guy is doing, and actually, yeah, you can reconstruct it indirectly in this way. Yeah. Any more questions? If you have a symmetric device, so he's asking if the additional protection is symmetric, left to right or not. And it depends if you have symmetry in your couplings or not. And if you have it's far. Come on. No, too much. Yes. So if you have this kind of a symmetry, that breaks the inversion. So you have a little bit of a different response. Yeah. Sure. That's fine. 1 or 2 years. Yeah. Maybe I don't want to make too optimistic promises. We're working towards within 2025, but you know. Now it's actually very close. So once you have the readout, you also have the initialization if you want. Or in any case, initialization is easy because you can go to a configuration and wait until it relaxes. The hard part is the qubit manipulation. And to do so, you need to be able to manipulate it very fast because the coherence time, you can read it here, of a two-side chain is about 10 nanoseconds. The predicted one is about 10 nanoseconds or so. So all your pulses need to be faster. And so you need to play a little bit with your craft. And I mean, it's doable to have pulses of a few nanoseconds. So it should be fine to observe Rabi oscillations. But then the problem is, if you read out in 40 microseconds, how are you going to see that? And there you can play tricks like, so when you, I'll do it very quickly. So if you have the 4 Majoranas making a qubit, 3 and 4, you get the Z gate when you couple these two, and you get the X gate when you couple these two. And say you read out in this basis. So what you can do is to initialize the system, then drive some Rabi oscillations in the X basis, and then turn it off. You did your like a Rabi experiment for a certain amount of time, and then you want to read it out. But your readout is 40 microseconds, and maybe even your Rabi, it's faster. So what you can do is to put a super strong coupling here, so that you lock the state in the Z basis, and therefore you have a little bit more time for readout. This you can play with this type of tricks and be able to read out even if your decay is. I left it here. Even if your decay is very fast. But then if this doesn't work, then we need to go to, so the first attempt is, of course, to do it with two-side chains. This is the shortest system. But if that doesn't work, we can always go to three-side chains. It will take a bit more time. And there the coherence should be long enough to do read out in any case. All right, So a few slides on the nanofabrication. I left it to the end because there are more pictures. You might be more tired, so maybe this is easier to follow at this stage. The goal is to go always from the room scale to the nanoscale, and we do that in several steps. This is an image taken with the phone of the lab. This is an image of the chip containing our devices, taken with the phone through a lens. This is an optical image, and this is an electron microscope image. And what I'm going to talk about is mostly this part, which is the one that is done in the clean room, dressed up like this. But at some point, yes, let's remember that even if I will talk mostly about this, let's remember that at some point you need to connect everything. So, to fabricate a Majorana qubit, what we need is, well, a semiconducting nanowire, also the ability to tune, and that's done with this pink gates in the bottom. Then we want superconductivity, and we want some metallic probes if we want to look at the density of states here and there. And we start from the bottom layer, which is the array of gates. And this shows an electron microscope image before anything else is added. And you can see that this this very finely spaced gates form a good, let's say, array. And that's done via lithography, electron beam lithography. Who has ever done it in their PhD life here? Only? Okay, then this is useful for real. Okay. Okay, the technique is quite interesting. You pick up a substrate, usually silicon. Then you put a polymer on top. And you put it inside a machine, this one, that shoots high energy electrons with a pattern that you define with your computer. So this defines the pattern that you want. And then you dissolve the parts that are exposed to the high energy electrons that come from this machine. Then you load everything into another machine where you can deposit metals. For example, for our gates, we use titanium palladium. 3 nanometers of titanium and that's 7 nanometers of palladium, so they're very thin. And in the end, you put the whole thing in acetone, and that dissolves these remaining yellow parts of polymers, and leaves you with this metal deposited in the bottom with the spacing that you defined. That's the technique, and that's the basis of all the clean room operations. Then, again, let's remind that we need to connect this to a bigger chip. This is the smallest scale. So this is about 3 micrometers of distance. And then everything becomes a bit bigger. And even bigger. This is the device size, which is 2 millimeters. This is something we can see. And these pads here are what we use to make actually the electrical connections. So to connect the small scale to the room temperature electronics. This is the chip, even bigger. This is something that we can handle with our tweezers in the clean room. And these pads here, these ones here, need to be very hard because we come there with wires and try to connect them, so we want a hard material. Tungsten is one of them, so we just do another lithography series and put tungsten to have these hard pads. And here you can see a picture of one of the devices where all the device with the pads, this is a different device design, but same concept, with all the pads are connected to the standard electronics via this thin wires. Okay, after the gates and the pads are done, we can deposit dielectric on top of everything so that our metallic gates do not touch the nanowire and do not leak electrons into our system. And we do that with a technique called ALD, atomic layer deposition, which is super cool because it's a chemical process that works in cycles of subsequent steps. So, for example, if we deposit halcium oxide, you first put a gas that has halcium on it until it attaches uniformly to the full surface. Then you take the halcium away, you put oxygen, you put actually water until the oxygen stays and oxidizes the full surface. Then take the water away, put halcium again, do another layer of halcium and then another layer of oxygen and so on, so that you build the whole dielectric layer by layer with a perfect stoichiometry and also a perfect uniformity. This takes quite some time since it's a layer, atomic layer after atomic layer. So like depositing 20 nanometers might take 6 hours. And then the tricky part for us was always to find a way to deposit aluminum in a good way on our semiconductor. And that's done with a technique that we developed over the years, which is called this shadow wall evaporation. The idea is that you put some walls and then deposit aluminum at a certain angle so that we get just a strip of aluminum here coming through this slit. And this is nice because it gives very sharp edges here and here that you do not get if you deposit aluminum everywhere and try to remove it selectively. That's why this technique is important for us. That's what gives this high definition and resolution for the aluminum strips. But to do so, we need to build the walls. And we do that still with lithography, but with a twist, because we do a double layer polymer. First, we put a standard resist, standard polymer, and do a lithography step. Then we put another one. This is basically silicon. And that fills all the holes. Then we do lithography again, so that we defined this top layer. And eventually, we remove in acetone the bottom layer, leaving these standing structures. And this is an image of the two layers. This is the yellow resist, and this is the green resist. Each of them is about 800 nanometers thick. This is an image of just the pillars. This is just spots. Whereas this is an image of the top layer. And this is an image of has a weird shape, but it's just to show you the idea of this shadow walls with some pillars here and 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 so on. And you can have very well-defined strips of aluminum. All right, now another tricky part. I have 10 minutes, I hope to be able to go through it. So we use the nanowires that our collaborators in Eindhoven provide, and they are grown chemically from gold droplets as a catalyst, and then they come up like beans. Building this, okay, this is in steps how the growth looks like. These are the gold droplets, and here after 1 hour they start to grow until they become a forest like this. And these are one of these forests seen from the top view with an optical microscope. So this is where the nanowire comes from, and our job is to pick it up from here and to put it on our sample with micrometer precision. And that's not super easy. Only a few people can do it in the whole building. And the main trick is playing a lot with the focus of the optical microscope to know your height. So for instance, here you can see this is the same substrate, but here you can see these lines of the gates. So you're in focus with the substrate, whereas here we are in focus with the shadow walls. And the gates are not visible anymore. So you play a little bit with the focus, and you understand at which height you are. And this is where you want to place the nanowire. This is 10 micrometers, and this is maybe 2. And we use this. This is an optical microscope. And it has a needle, and it can be controlled with this, with these knobs in all 3 directions. And it's quite tricky because the nanowires are 100 nanometers thick, and light is thicker. So light goes from 300 to 700, the visible light. So seeing all of this under an optical microscope is quite challenging. You can barely see the nanowires. And here I show you a video of how we approach the substrate and attach a nanowire. And the idea is the following. You have the nanowire like this, and you come with your needle next to it and try to pick it up with van der Waals forces. So now this is the substrate with all the forest. Now we are in focus with the substrate, and the needle is coming down and down and down and down. Okay, now they are the same height. And we try to pick up one of the nanowires. It doesn't come. This is quite frustrating, I can tell you. Still doesn't come. And now the video takes a few minutes, but it might take more. Okay, it moved, so at least we detached from the substrate, but it's still attached to it, in this case. You need to follow this, this spot here. Okay, and now the spot disappeared, so it means that it's not in focus with the substrate anymore. We successfully picked it up. So the nanowire is with the needle here. It's vertical, like this. And we want to rotate it 90 degrees to be able to deposit it. So we do so. And that's an image through the lens of the optical microscope that shows the nanowire. And this is the cross that you have on the microscope itself that you can use to align. Then you align it to you align the same cross to the substrate so that you know that the nanowire has the same direction of the substrate as well. And then what you want to do is to approach this substrate with this nanowire as close as possible to your shadow walls and leave it there. And no. Please, no. The video doesn't work. That's sad. Yeah, okay, it does. Okay. Now again, you play a lot with the focus. Now you're in focus on the shadow of the needle. Change magnification. Now you are focusing on the needle with the nanowire. You can sometimes barely see. There. And now slowly you're moving the Z control down so that the needle comes to the substrate. Okay, this is the target landing point. You want to be as close as possible to these structures. and it's very hard to put the nanowire directly on top. So normally, we put it slightly next to it, and then we push it on top. And now I will show you that as well. Okay, the nanowire is coming. Again, you play a little bit with the focus. Now they're quite close, because you can see both the needle and the substrate in the same image. You can see the needle and the shadow of the needle. Done. Now the nanowire landed on this slightly yellow thing, a little bit snaky, it is there. And it's almost at the target position. We just need to push it on top of the metallic gates. And to do so, we use this technique. So the nanowire is landed like this, and we come with the needle like this and push it. Now I'll show you the video of this last operation. This is also very frustrating because sometimes the nanowire breaks, as you will see. There, that's a piece of nanowire broken on the side, but the rest is fine. And you approach it from one side, push a little bit, and go up. There you go, so that it stays quite straight. And once you learn the craft, you can do it quite reproducibly. There was a colleague of mine who got super skilled with it, and he could successfully put like 10 nanowires in series with a 100% success rate. And he used that to make devices that actually used 10 nanowires. And there you go. The nanowire is pushed on top of the gates, and you see that the contrast changes. We pushed it a little bit more because the width of this yellow piece, which are the gates, is roughly how long the shadow is. So we want the nanowire to be within it so that we have a strip of aluminum before the rest of aluminum everywhere else. All right. That was the nanowire deposition. I have only a few minutes, but they should be enough. Then the next thing is to put the superconductor on top. So we load it into this machine here, which is another metal evaporator. And here the tricky thing is to remove the native oxide on the surface of the nanowire. This is very tricky. It requires careful calibration, and it required 2 years to get to the right parameters for the first time. And after 10 years of successful devices, we had to recalibrate it again, and it took another year. And the idea is that you shoot protons on top of your surface, and that reacts with the oxygen, forming water and leaving your semiconductor pristine. And it's a chemical type of removing the oxide, so it's relatively clean. And after this is done, and needs to be done at the right temperature and for the right amount of time, then we can deposit aluminum at the 30 degrees angles, so that a few facets of the nanowire are covered, like this. And you need to play a lot in it with the temperatures to get the good removal and to get the good growth of aluminum, and that's what takes time to calibrate. Because you make a sample, then you measure it, and every sample maybe takes a week or so. So if you want to do some iterations, it takes a little while to get to the right parameter spot. And here I can show you a TEM of one of such devices. This is the nanowire, and this is the aluminum on top. And in blue, you see oxygen. You can see the oxygen also here in the substrate. This is aluminum oxide and silicon oxide here below. So all the blue is oxygen. And if you take a cut along this direction, you see that there is oxygen at the in the external interface between the aluminum and the vacuum. But there is no oxygen here in between the aluminum and the indium antimonide, which is what we want. All right, and then the reason for having a double layer shadow wall is the fact that then you can come with the same needle used to deposit the nanowire and use it to kick the smart wall off. So you get here close with the needle and remove the shadow mask. And this is what's left. This is the shadow. So within this shadow, there is no aluminum, apart from this strip that comes to the device like a victory shape. And these are the pillars of the shadow walls that you can see here. And there is aluminum everywhere else. So we actually want at some point to get rid of it. But first, we do one more lithography step and deposit the normal metal contacts to the sides. And now finally, we remove the aluminum by doing yet another lithography step. This is the device with the aluminum everywhere and the contacts already. Then we put a mask here to protect this part of the device, and we remove aluminum everywhere else. And this is the chip with the removed aluminum. So this is aluminum, and the rest doesn't have it. And this is basically all the stacks of this fabrication. The time is up, but it's good because I just reached my conclusion. I just want to thank once more all the colleagues that made this possible. And I want to thank you for your attention. And if you have any further questions, you can maybe ask one quick now, and then in the next days, I will be here this afternoon and also tomorrow, for sure, for the full morning. So don't hesitate to reach out and ask a deeper or shallower question, whatever you like. Thank you. Yeah, for us, any spin orbital coupling is fine. It does happen that it gets a little bit strained, not twisted, because somehow the van der Waals forces want a facet to be fully with full adhesion. So that doesn't happen. But what happens is bending. So if you, and that's why we push it like this. So coming close and then moving the needle up so that it gets quite straight. If you push it like this, then it gets very bended. And indeed, you get weird stuff. I think there is a paper from our group from like 20 years ago or so when they studied what happens to carbon nanotubes once they're bended. And I guess it's similar physics. Any other questions? I don't want to keep you here over time, so if we want to close, it's also fine.
First, thank the speaker again. Now I think it's time for the coffee break. The coffee break will be in another building, in the closer building, but you can follow us, and that's all.
Hola, hola. Hola, 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 hola.